For decades, the foundational rule of IT infrastructure was rigid: one machine, one operating system. If an organization needed to deploy a new database or email server, they had to procure a physical box dedicated exclusively to that task. As networks expanded, this one-to-one ratio created logistical bottlenecks. Every new application required purchasing, powering, cooling, and finding rack space for a brand new piece of hardware. This approach was also inefficient. A single application rarely requires the full processing power of a modern machine. In a traditional setup, a dedicated server might only use a fraction of its CPU and RAM, leaving the majority of its computing capacities sitting idle. Beyond wasted hardware, IT departments faced software constraints. As operating systems updated, essential legacy applications, like tools built exclusively for Windows XP, often refused to run on modern architectures. Organizations were forced to keep outdated hardware running just to support a single program. Testing software presented a similar risk. Installing unpatched code, beta applications, or investigating suspected malware directly on a production machine could compromise the entire system. To solve this hardware waste and bypass these software limitations, the IT industry had to break the one-to-one rule. They needed to decouple the operating system from the physical box, a concept known as hardware abstraction. The mechanism that makes this abstraction possible is a specialized software layer called a hypervisor. A hypervisor sits above the physical components, the CPU, memory, and storage, and emulates them. By providing multiple operating systems with their own virtual hardware, the hypervisor allows multiple virtual machines, or VMs, to operate simultaneously on a single host. This graphic breaks down hypervisor architectures, starting on the left with Type 2. In a Type 2 configuration, physical hardware runs a standard host operating system, like Windows. The hypervisor is installed directly on top of that host OS. This architecture is standard for client-side virtualization on employee workstations. It allows a user to spin up isolated VMs to safely test software in a sandbox or run legacy Linux applications alongside their normal Windows environment. However, because every command from a Type 2 virtual machine has to travel through the hypervisor and the underlying host operating system before it reaches the CPU, it introduces latency. That overhead makes it unsuited for a large data center. For enterprise environments, infrastructure relies on Type 1 bare metal hypervisors, shown on the right. In this model, the host OS is removed, and the hypervisor installs directly onto the physical hardware, providing more efficient, direct access to resources. The hidden performance cost of traditional virtualization lies inside the VM structure. To run an application, a virtual machine must boot its own complete, independent operating system, referred to as the guest OS. This illustrates the resource strain. Because each guest OS operates in isolation, memory must be rigidly partitioned. If you allocate 6 GB of RAM to a VM, that memory is locked away from the host, regardless of whether the application is actively using it. When hosting hundreds of applications, the hardware becomes bogged down by the redundant guest OS environments running simultaneously. To eliminate this bloat, developers use containerization via platforms like Docker. This diagram compares traditional VMs on the left with modern containers on the right. Looking at the traditional stack, every application requires its own duplicate guest OS block. On the right, the container architecture removes the guest OS. Containers package the application code and its specific dependencies, and they all run by sharing the host machine's single OS kernel. By sharing the kernel, containers eliminate rigid memory partitioning. They operate with lower overhead, feature faster startup times, and provide a consistent execution environment from testing through to production. Removing the heavy guest OS changed the utility of abstraction, shifting virtualization from a resource-intensive emulation tool into an optimized engine capable of massive scale. The next step is taking thousands of these bare metal hypervisors and container engines and networking them across global data centers. This shift creates cloud computing, transitioning IT infrastructure from static, physically owned assets in a local server room to internet-based on-demand services. The National Institute of Standards and Technology defined several characteristics for a true cloud environment. The first is broad network access. These abstracted resources must be accessible from any device over the internet. Next is resource pooling. Providers use virtualization to build multi-tenant environments. This allows many different customers to securely share the same physical data center hardware. Because the hardware is abstracted, the cloud offers rapid elasticity. If traffic spikes, the infrastructure automatically scales up by provisioning new virtual servers and containers in real time, then scales back down as demand subsides. Finally, all of this is delivered as a measured service. Instead of purchasing server racks up front, organizations use a metered pay-as-you-go model, paying only for the compute cycles, storage, and bandwidth they consume. The cloud is hardware virtualization executed at scale, converting computing power from a fixed capital expense into a flexible utility. Because the cloud abstracts the physical hardware, organizations must define the shared responsibility model, the boundary where the cloud provider's management ends and the client's begins. This boundary is defined by 3 primary service models, structured here as a pyramid. At the base is Infrastructure as a Service, or IaaS. In this model, the provider manages only the physical servers, storage, and networking hardware. With services like AWS EC2 or Azure Virtual Machines, the client remains responsible for installing the operating system, maintaining patches, and deploying applications. IaaS is suited for clients who require total control over their operating environments. Moving up the stack is Platform as a Service, or PaaS. Here, the provider manages the physical hardware plus the operating system and development environment. PaaS is designed for software developers. By outsourcing server maintenance, a team can focus entirely on writing and deploying code using ready-made frameworks. At the top is Software as a Service, or SaaS. In this model, the provider manages the entire stack, from the data center hardware to the final application interface. Applications like Microsoft 365, Salesforce, and Dropbox are SaaS. They deliver ready-to-use software via the internet, with no local installation or back-end maintenance required. Choosing between these models is a decision about how far up the abstraction stack an organization wishes to outsource its IT administration. Hardware abstraction is the core concept that supports modern IT infrastructure. At the local level, Type 2 hypervisors grant technicians the flexibility to build secure sandboxes, safely testing code and maintaining legacy systems without risking their primary workstations. At the application level, containerization addresses the resource bloat of traditional virtual machines, sharing the host OS kernel to create the high-speed architecture required for modern software. And at the global scale, cloud computing takes these abstraction technologies and pools them, offering enterprises elastic resources on demand. By mastering these layers, from bare metal hypervisors to massive SaaS deployments, IT professionals bypass the physical limits of hardware to build systems that scale as demand requires.